you're going to look at page 9. We were taking a look at that photoelectric switch and how it was going to sense infrared light versus visible light. Okay, the switches. So the answers were they detected the presence of the objects, the presence or absence of light. We already did that. Light sensing objects, presence of light to operate senses. Dark sensing, the absence of light. Right. 3 types went over them. They're the through beam direct, retroreflective, which requires a shiny surface, and diffuse, which just uses the natural pop properties, right? We talked about the gain on the amount of light available above what is needed to activate the switch. So we'll talk about gain in a minute to activate it and deactivate it. The operating point and releasing point is hysteresis, and once again I'll touch on that again in just a minute, okay? The term sourcing means it supplies plus DC to a load, and there's also sinking that will go to it, but our switches were delivering voltage, okay? How does light get to the receiver when using a different type of switch? It bounces off the target. So that was the first part. Everybody did pretty well on it. The next one was a polarized retroreflective switch, and what I was talking about, I told you I would give you a little bit more of a description of this, and on page 12 you can take a look at it. And so basically it's like a fence here, okay? So when this light comes shining through this fence, you know, this light, you see the arrows left, right, up, down, so it's hard for me to draw, but there's light coming out, running up, it's straight up and down like this, and some of the light runs perpendicular to it, and some of the light runs at 45 degrees to it. I mean, this light is just flying all over directions. It's in a wave, okay? It's still light, it's in a wave, but look at, who says that it would be flat on the paper? Well, you know, why couldn't this be rotated 90 degrees or 91 degrees or 92 degrees or whatever, okay? So what this is, it's like a little fence, and what it does is any light that's traveling flat like this gets through, but any light that's traveling, I guess, up and down like that, it gets blocked because it would come through only as a straight line, because that fence would block it, okay? And so what you have is the light source over here is set to capture light only coming in that direction, okay? So it's looking for flat light, so it's polarized light, and so depending on what comes off of here, once it reflects, it still remains polarized, and then therefore it stays, in this case, flat on the surface, and so this wouldn't catch it. You would have to rotate this 90 degrees for it to catch it, okay? And so another example that I gave was in your windows in your house, where if you're in a big sub, in your bathroom window, the light is polarized this way, and if you look across to your neighbor's house, their window is polarized this way. So if you look out your window, you can't see into your neighbor's bathroom, and the neighbor can't see into your bathroom. But if the neighbors, if they installed the windows wrong and had them installed polarized that way, well then you could see right into your neighbor's bathroom. So that's kind of the way that polarized light was working, okay? And so that's what that sensor was about. And so the next one was page 16. Here's what we got here. You notice that it was requiring a depolarizing reflective surface. You know, just because it was bouncing the light off doesn't mean that it was catching it. It was looking for light to be all, you know, in one direction, okay? And then once again we did the same thing here, so that's how that polarized was worked. It's made to detect items that the light has been polarized. So here were the answers. Your hand blocked the light so it could not return to the receiver because a photoelectric switch detected the presence of light. Plastic bag does not block red light. Wire is not thick enough to block the light. That's what we were talking about earlier with that convergent beam, that if it's not thick enough, it won't work. And so if you want to do something thin like a needle, then you need to take that light from this sensor and you need to converge it to that certain point, and then it would be okay. But otherwise, if you put that here, that wire here, this was too wide, it wouldn't block it. Reflector can still reflect the light back to the sensor. Okay, and so the next one was page 18 for Which applications generally where a part can block most of the sensing beam? That's where you'd use it. Where the part can block most of the sensing beam, you would use this retroreflective, okay? Because it's kind of just looking for a certain amount of light or presence of light, not that you're going to take the whole beam and block most of it, okay? And worry about the width of this beam here. Name 2 reasons why polarized visible red light. Polarizing filters cause losses. 2 purposes are filter and polarize. The corner cube reflector. Small targets do not block the sensing beam. Excess greater than 2.5. Okay. Once again on these, if you want to go back on these at the end, we can review these and talk a little bit more. So we're moving fast here. Background photoelectric characteristics. That was page 22. So it detected all the stuff, right? And it says here, does it detect the plastic bag's presence? Yes, no. The sensor can sometimes detect it. Transparent targets are hard to detect. They are. So sometimes you got to mess around with it. Shiny metal was dependent on the angle that the light hits the beam. Okay. Target was too small, and the pencil blocks the light. Place your pencil, and is it? Yes, pencil blocks the light. Review questions were short-range applications where the background is very close to the target and the background is highly reflective. Okay, looking for reflection there, right? Background is very close to target and the background is highly reflective. Want to differentiate the two. How do background suppression switches ignore the background behind the target? The switch does not ignore the background. Instead, it uses 2 sensors and sophisticated electronics. By comparing the 2 signals, the sensor screens out the background from the target. And so that was that third item that I was kind of describing on the homework, is that you're looking for the difference, okay? Background suppression, the 2 active sensitive elements are calibrated to detect lights in front and behind. And what is the distance? About 10% of the maximum sensing distance. Okay, moving on, getting there, a couple more. The next one's capacitive proximity switch, which dealt with dielectric constants. And so we had the capacitive sourcing PNP, which means it was producing voltage. Okay. And then we had, did good. It was pretty much detecting everything here. Okay. Remove the reflective block, place your hand, no. Determine which of the following materials are sensed or not. So here, white paper, styrofoam, clear plastic, and didn't have enough of a dielectric constant to get these things, but it did get all those. But then I think we went ahead and did some review questions. So I'm looking at page 31, and it was dielectric constant greater than 1.2 is what it 2 parameters were the size of the probe, the size of the target. Also the material dielectric constant, the temperature, humidity, shielded or not. Those are things that affect it. Explain why capacitive pressure sensing face must be spaced away so it does not detect them, right? We don't want to place next to each other because the sensing fields will interact with each other. Okay. Most are equipped with a sensitivity to compensate for target and application. So you can adjust the sensitivity to get that sensor to sense. So those are the things that I'm getting there. I think we have one more page of this. And characteristics of an inductive prox. I'm looking at page 36. And the inductive was getting the metal. It wasn't getting the non-metal. So it needs that. And then what we did is we did some other ones here. And it didn't get the magnet, but it's got these other ones. It's got the aluminum, copper, things like that. Okay? And this was kind of weird. Is there a difference? Which one has the longest sensing distance? The thin aluminum. You're like, well, why not the thick aluminum? Well, it might be the type of aluminum that this has a different dielectric constant. This might not be the same types of aluminum. Okay. The magnet is not made of metal, so no eddy currents could be set up in it. And magnetic field is not the same. That's a sensor. Okay. And then it said measured distance is about 1/4 inch. Okay. I think that's how we were doing there. Review questions. What causes The maximum sensing distance of an inductive proximity switch should be relatively short. Magnetic field associated with occurrence is quite small, so don't have very long sensing range. Nearby metallic surfaces may be sensed. Magnetic fields from other sensors may be sensed. So that's why they must be spaced from surrounding metal surfaces. Okay, you don't want the sensor interacting with itself. Name two parameters: the size of the sensor, the size of the target. What type of materials are detected? Metals. Was your finger not detected? Your finger is unable to disrupt the magnetic field or the eddy current. Nope.